Last time we did the Icy Hot Lab, we took a beaker of ice water and we put it on the hot plate and heated it until the water boiled. And we broke it into three, the graph can be broken into three little sections, A, B, and C. A down there is a little plateau where you still have solid water mixed in with the liquid water. And the temperature wouldn't rise, even though for that entire time you were adding energy, you were adding heat to it, its temperature wouldn't increase. That's because in region A, all the energy you were putting into it was going to melt the ice. It wasn't raising the temperature of anything. It was changing the phase from solid to liquid. Once that last ice chip melted, it was all liquid. Now the energy was going into being stored thermally, and it was raising the temperature of the water, making the water particles move faster. We get all the way up to C. Once the water starts boiling, the energy you're adding from the hot plate isn't going to increase the temperature anymore. It's going to change the phase again from liquid to gas. So we're going to start to note how we're storing energy in the system and how we're transferring. Obviously, the energy was being transferred from the hot plate to the water, but in these different regions, like in A, it was being stored as phase energy. It was changing the phase from solid to liquid. In B, it was being stored thermally in the water by making the particles move faster. And in section C, it was being stored as phase energy. Again, it was being used to change the phase of the water from liquid to gas. And now I'll talk to you a little bit about energy bar charts. You'll get to know them as LOL charts, and you'll see why in a minute. This is how we can show how energy is transferred and how it's stored in a system, basically, in a chemical. Now, first of all, the vocabulary. You did a reading while you were doing the lab, and we talk about energy transfer, and there's three ways that we're going to talk about in science: work, heat, and radiating. We're not really worried about working, that's making things move, and we're not really worried about radiating. We're just worried about heating, transferring energy in the form of heat, and also how energy is stored: chemical, phase, and thermal. And odd as it sounds, in chemistry class right now, we're not worried about chemical energy storage. We're worried about how it's stored as its phase, solid, liquid, or gas, and how it's stored thermally. That's the motion of the particles. And we have to keep what makes our math easy here on these LOL charts is understanding that energy is always conserved. You can't create or destroy. Whatever energy is in the system or put into the system is always somewhere. It'll be there and can always be accounted for. Okay? Now, phases are just another way of saying solid, liquid, and gas. And phase changes are boiling or condensing. So if you're moving left to right on this, this is called an energy curve or a heating cooling curve. These two flat plateaus are where the phase changes are going. There's no temperature change in here. It's boiling or condensing, melting, or freezing. And that's at the two plateaus. And the most important thing to note is that there is no temperature change while you're boiling or while you're melting or freezing water or any other substance. Our heating and cooling curve can tell us a lot. It can tell us that stuff is being melted or boiled. There's no temperature change, and this is where when you put in energy, energy is being stored as phase change. You're literally, all the energy you put into it is put into melt it or freeze it or boil it. No temperature change. In the other regions, this is where energy is being stored thermally, where the particles are moving faster if you're heating or slower if you're cooling. And that's down here in regions between A and B, C and D, E and F. So we have solid, liquid, and gas phases. Let me give you an example of a bar chart. Okay, so we have a cup of hot coffee that cools as you set it on the table. So you just take the cup of coffee, you set it on the table. We all know it's going to cool down, but we're going to try to quantify the energy, how it's transferred and how it's stored. So first of all, right in the center, I think you can see why this is called an LOL chart. You're going to write the system. Okay, our system is a cup of coffee. We're not going to deal with other things in the system, the table or anything else, just the cup of coffee. Everything else is the surroundings. The second one, we're going to decide, we're going to work from from the inside out. We're going to look at chemical change. We're going to decide if there is any chemical change that we need to worry about, any energy of chemical. Well, it starts as a hot cup of coffee and it ends up as a cool cup of coffee. Well, there's no chemical change because it's still a cup of coffee. So we're going to ignore chemical change. And we're going to ignore chemical change this whole unit. We're just going to deal with phase and thermal. We're going to assign values to phase energy. Well, it's a hot cup of coffee that sits on the table because of a cool cup of coffee. First of all, let's talk about what kind of energy we can give to phase. Due to interactions between particles, and I know this should be sort of intuitive, you should know this. Solids have less energy than liquids, and liquids have less energy than gas, because we're just talking about basically its temperature and therefore the motion of the particles. Solid particles have less energy than liquid, which have less energy than gases. So we're going to choose to always give solids 1 bar, always give liquids 2 bars. Remember, these are energy bar charts. And we're going to give gases 4 bars. Always. No choice here. If what you're dealing with is a solid, it's 1. If it's a liquid, it's 2 bars. If it's a gas, it's 4 bars. So we're going to go back to our example. And we start with a hot cup of coffee as it sits on the table. It cools as it sits on the table. Well, it's hot coffee. That's a liquid. So we're going to go ahead and give it 2 bars of phase energy. 2 bars because it's a liquid. And then that's the initial conditions. The final conditions on the right, well, it ends as a cool cup of coffee. It didn't freeze. It's still a liquid, so it's going to get 2 bars. So at least as far as phase energy, we've had no change. It starts as a liquid and it ends as a liquid. Okay, now we'll talk about thermal energy. Well, it starts as a hot cup of coffee. And if you'll notice that the first sort of line in the initial and final phases, we like to think of as 0 degrees Celsius, the freezing point of water, and 2 bars as being room temperature. Then 3 or 4 bars would be obviously warmer and hotter. Well, okay, so it's hot coffee. We certainly don't want to say that it's room temperature. Let's give it 3 bars. You have a choice here with thermal. You could have given it 4 bars. That's fine, but I'm going to give it 3. And it cools to room temperature, so it ends up at, I'll say, 2 bars. Okay. So now you can start to see that we had some energy initially, and in the final stages, we have less energy. Okay. Now we're going to show how it was transferred, and we have to keep into account the conservation of energy. If we started with 5 bars, we ended with 4. That means we must have lost a bar of energy. The law of conservation of mass is we couldn't have destroyed it. It's gone somewhere, and we're just going to draw that 1 bar as having left the system. So we're going to draw it as an arrow pointing out of the system in the middle. Okay, so let's talk about another example here. A tray of ice cubes, something with a phase change. A tray of ice cubes at -8 Celsius, below the freezing point of water, is placed on the counter and becomes water at room temperature. So we know in this case, instead of losing energy, this is gaining energy. These ice cubes are absorbing heat from the surroundings, warming up and melting. So what we know is that the system is a tray of ice cubes. It's solid water that turns into a liquid. So there's no chemical change. It started as water and it ended as water. We know that the phase energy must increase because we started as solid, that's 1 bar, and became a liquid, 2 bars of phase. We know the thermal energy increased because it started at -8 Celsius. It must have warmed up because it's turned to above freezing liquid. And so we started we're going to say with a total of 1.5 bars in the left of the arrows and ended up with a total of 4 bars. So we must have gained 2.5 bars. Not real energy numbers. We're not quantifying joules yet, just saying relatively. We started with one, we're going to say 1.5 bars. We added 2.5 bars from the surroundings, and we have 4 bars of energy. So let's see what that looks like in a bar chart. Notice on the left, in the initial conditions, it wasn't even 0, so I'm going to give it half a bar of energy. Thermal energy, 1 phase bar because it's a solid and all solids get 1. In the middle, we're saying we absorbed 2.5 bars of energy. So we ended up with a room temperature liquid, 2 bars of thermal and 2 bars of phase.